welcome to another topic in material science and engineering. Today, we will discuss corrosion prevention and control. Why study corrosion and degradation of materials? With the knowledge of the types of and understanding of the mechanisms and causes of corrosion and degradation, it is possible to take measures to prevent them from occurring. For example, we may change the nature of the environment, select a material that is relatively non-reactive, and/or protect the material from appreciable deterioration. Thus, by the end of this lesson, you should be able to distinguish between oxidation and reduction electrochemical reactions, describe the nature of the deteriorative process for each of the 8 forms of corrosion and hydrogen embrittlement, and denote the proposed mechanism. List 5 measures that are commonly used to prevent corrosion. Explain why ceramic materials are in general very resistant to corrosion, and discuss the 2 degradation processes that occur when polymeric materials are exposed to liquid solvents, and the causes and consequences of molecular chain band rupture. This will be the outline of my presentation. Let's first start with corrosion versus degradation of materials. Most materials experience some type of interaction with a large number of diverse environments. Such interactions impair a material's usefulness as a result of the deterioration of its mechanical properties, physical properties, or its appearance. Deteriorative mechanisms are different for 3 different types of materials. In metals, there is an actual material loss either by dissolution or corrosion, or by the formation of non-metallic scale or film oxidation. Ceramic materials are relatively resistant to deterioration. For polymers, mechanisms and consequences differ from those for metals and ceramics, and the term degradation is most frequently used. Polymers may dissolve when exposed to a liquid solvent or may absorb the solvent and swell. Also, electromagnetic radiation, primarily ultraviolet, and heat may cause alteration in their molecular structures. Now that we understood the difference between the term corrosion and degradation of materials, let's dig deeper to corrosion. Corrosion is defined as the destructive and an intentional attack of a metal. It is electrochemical and ordinarily begins at the surface. Note that we will define the term electrochemical later. The problem of metallic corrosion is one of significant proportions. In economic terms, it has been estimated that approximately 5% of an industrialized nation's income is spent on corrosion prevention and the maintenance or replacement of product lost or contaminated as a result of corrosion reaction. Thus, corrosion is really a big concern. What does electrochemical means? For metallic materials, the corrosion process is normally electrochemical. It is a chemical reaction in which there is a transfer of electrons from one chemical species to another. Here, metal atoms characteristically lose or give up electrons in what is called an oxidation reaction. Examples in which metals are oxidized are in the oxidation of iron, as well as in aluminum. Now that we understand what corrosion is and how big concern it is, let's try to understand the different forms of corrosion. It is convenient to classify corrosion according to the manner in which it is manifest. There are 8 forms of metallic corrosion, namely uniform attack corrosion, galvanic corrosion, crevice corrosion, pitting corrosion, intergranular corrosion, selective leaching corrosion, erosion corrosion, and stress corrosion. Let us discuss them in detail, beginning with the uniform attack corrosion. Uniform attack corrosion is a form of electrochemical corrosion that occurs with equivalent intensity over the entire exposed surface and then leaves behind a scale or deposit. In a macroscopic sense, the oxidation and reduction reactions occur randomly over the surface. Some familiar example includes the general rusting of steel, as you can see here in the photo, and iron and the tarnishing of silverware. This is probably the most common form of corrosion. One way to prevent uniform attack corrosion is the proper selection of the material for a particular application, knowing the kind of environment that the material will be exposed to. We will discuss this later on in the subtopic prevention. Let's move forward to the second form of corrosion, the galvanic corrosion. Galvanic corrosion occurs when two metals or alloys having different compositions are electrically coupled while exposed to an electrolyte. The less noble or more reactive metals in the particular environment will experience the corrosion. The more inert the metal, which is the cathode, will be protected from the corrosion. For example, steel screws corrode when in contact with a brass in a marine environment. Or if copper and steel tubing are joined in a domestic water heater, the steel will corrode in the vicinity of the junction. You can also find the image here which depicts what happened in a galvanic corrosion. You can see here that only part of the metal that is connected to the corroding material has corroded, but the metal surface is not uh, undergoing the corrosion. This is because of the two metals, this bolt and nut area here is the less noble or the more reactive in the in this particular environment. Some ways to prevent and control galvanic corrosions are: if coupling of dissimilar metal is necessary, choose two that are close together in the galvanic series. You can find the galvanic series in the internet and see the relationship between the metals, how close they are in that table in the galvanic series. Avoid an unfavorable anode to cathode surface area ratio. Use an anode area as large as possible. Electrically insulate dissimilar metals from each other. This is a form of a cathodic protection. Let's proceed to the third form of corrosion, the crevice corrosion. Crevice corrosion is an electrochemical corrosion occurring because of concentration differences of ions or dissolved gases in the electrolyte solution and between two regions of the same metal piece, as you can see here in the illustration. A good example of this type of corrosion occurs in crevices and recesses or under deposits of dirt or corrosion products where the solution becomes stagnant and there is a localized depletion of dissolved oxygen. This is an illustration of the mechanism of crevice corrosion between two riveted sheets. As you can see here in the uh, larger view of this section of the riveted sheets, you can find that in between the surfaces, there's actually crevice corrosion happening. Crevice corrosion may be prevented by using welded instead of riveted or bolted joints, using non-absorbing gaskets when possible, frequently removing accumulated deposits, designing containment vessels to avoid stagnant areas and ensure complete drainage. In this way, we can prevent or control the occurrence of this kind of corrosion. Let's move forward to the fourth forms of corrosion, the pitting corrosion. Pitting is another form of very localized corrosion attack in which small pits or hole forms. They ordinarily penetrate from the top of the horizontal surface downward in a nearly vertical direction. It is an extremely insidious type of corrosion, often going undetected and with very little material loss until failure occurs. The mechanism for pitting is probably the same as for crevice corrosion in that oxidation occurs within the pit itself, with complementary reduction at the surface. An example of pitting corrosion is shown here in the surface. You can see here the formation of pits in the material. To prevent and control this kind of corrosion, we must avoid scratching of the metal because a pit may be initiated by a localized surface defect such as a scratch or a slight variation in the composition. We should use metals with polished surfaces whenever possible because it has been observed that specimens having polished surfaces display a greater resistance to pitting corrosion. And finally, we should alloy metals whenever possible because stainless steels, for example, are somewhat susceptible to this form of corrosion. However, alloying with about 2% molybdenum enhances their resistance significantly. Let's move forward to the fifth forms of corrosion, the intergranular corrosion. Intergranular corrosion occurs preferentially along the grain boundaries for some alloys and in specific environments. The net result is that a microscopic specimen disintegrates along its grain boundaries. This type of corrosion is especially prevalent in some stainless steels. When heated to temperatures between 500 and 950 for sufficiently long period of time, these alloys become sensitized to intergranular attack. This schematic illustration shows chromium carbide particles that have precipitated along grain boundaries in stainless steel and the addendant zone of chromium depletion. You can see here the formation of the grain boundaries. Stainless steel may be protected from intergranular corrosion by the following measures: subjecting and the sensitized material to a high temperature heat treatment in which all the chromium carbide particles are redissolved, because this chromium carbide is actually the one that causes this formation of these granular attacks. Lowering the carbon content below 0.03% by weight carbon so that carbide formation is also minimal. Alloying the stainless steel with another metal such as niobium or titanium, which has a greater tendency to form carbides than does chromium, so that the chromium remains in solid solution. In this way, we can prevent the formation of the intergranular corrosion. Let's move forward to selective leaching corrosion. Selective leaching is found in solid solution alloys and occurs when one element or constituent is preferentially removed as a consequence of corrosion processes. The most common example is the dezinctification of brass, in which zinc is selectively leached from the copper-brass alloy. The mechanical properties of the alloy are significantly impaired, since only a porous mass of copper remains in the region that has been dezinctified. An example is shown here in the illustration. Let's move forward to the seventh type of corrosion, the erosion corrosion. Erosion corrosion arises from the combined action of chemical attack and mechanical abrasion or wear as a consequence of fluid motion. Virtually all metal alloys, to one degree or another, are susceptible to erosion corrosion. Relatively soft metals such as copper and lead are also sensitive to this form of attack. It can be identified by surface groove and waves having contours that are characterized of the flow of the fluid, as you can see here in the illustration. Propellers, turbine blades, valves, and pumps are susceptible to this form of corrosion. It is also commonly found in piping, like in areas like bends, elbows, and abrupt changes in pipe diameter, positions where the fluid changes direction and flow suddenly becomes turbulent. Thus, in order to prevent and control this, we must reduce the fluid velocity because it decreases the rate of the corrosion. Also, we should also be careful in the nature of the fluid because it has a dramatic influence on the corrosion behavior. We can also change the design to eliminate fluid turbulence and impingement effects because these are also contributory factors to this kind of corrosion. Other materials may be utilized that inherently resist corrosion. Also, removal of particulates and bubbles from the solution to lessen its ability to erode. Finally, we have stress corrosion. Stress corrosion results from the combined action of an applied tensile stress and a corrosive environment. Small cracks form and then propagate in a direction perpendicular to the stress, with the result that failure may eventually occur. Failure behavior is characteristic of that for a brittle material even though the metal alloy is intrinsically ductile. Furthermore, cracks may form at relatively low stress levels significantly below the tensile strength. In order to prevent this kind of corrosion, we must lower the magnitude of the stress, reducing the external load or increasing the cross-sectional area perpendicular to the applied stress. An appropriate heat treatment may be used to anneal out any residual thermal stresses. Another important consideration in the prevention of corrosion and degradation of material is the term hydrogen embrittlement. Various metal alloys, specifically some steels, experience a significant reduction in their ductility and tensile strength when atomic hydrogen penetrates into the material. That is also the reason why you must carefully select the kind of material that will be used, especially in application where it will be exposed to water environment. In relation to that, we will discuss the different corrosion environment. Corrosive environments include the atmosphere, aqueous solutions, soils, acids, bases, and organic solvents, molten salts, liquid metals, and last but not the least, the human body. These are the environments that causes the happening or occurring of the corrosion. On a tonnage level or basis, the atmospheric corrosion accounts for the greatest losses. Moisture containing dissolved oxygen is the primary corrosive agent, but other substances including sulfur compounds and sodium chloride may also contribute. This is especially true in a marine environment atmospheres, which are highly corrosive because of the presence of sodium chloride or salt. Dilute sulfuric acid solutions or acid rain in industrial environments can also cause corrosion problems. If you can notice, in areas near seaports, there are you can see also the occurrence of corrosion, for example, in some metals that are very near this marine environment. This is attributed to this kind of environment in atmospheric corrosion. Metals commonly used for atmospheric applications include alloys of aluminum and copper and galvanized steel. So if you have to choose the kind of material that can be used in order to minimize or prevent the occurrence of this kind of corrosion, we should consider these materials instead. Aqueous solution is also another corrosion environment. Water environments have a variety of compositions and corrosion characteristics. For fresh water, normally contains dissolved oxygen as well as other minerals, several of which accounts for hardness. Seawater contains approximately 3.5% salt, predominantly sodium chloride as well as some minerals and organic matter. Seawater is generally more corrosive than fresh water, frequently producing pitting and crevice corrosion. Thus, cast iron, steel, aluminum, copper, brass, and some stainless steels are generally suitable for freshwater use. Titanium, brass, some bronze, copper, nickel alloys, and nickel chromium molybdenum alloys are highly corrosion resistant in seawater applications. Soil is also another corrosive environment. Soils have a wide range of compositions and susceptibility to corrosion. Compositional variables include moisture, oxygen, salt content, alkalinity, and acidity, as well as the presence of various forms of bacteria. Cast iron and plain carbon steels, both with and without protective surface coatings, are found most economical for underground structures. So if you have to use metals for underground structures, then you can use this kind of materials or consider this kind of materials. Let's move forward to the ways how we can prevent corrosion. Perhaps the most common and easiest way of preventing corrosion is through the judicious selection of materials once the corrosion environment has been characterized. So we learned in the previous slide the different corrosion environment. Once we already have an idea what kind of environment the material will be used, then we will have to be judicious in the selection of the materials. Standard corrosion references are helpful in this respect. There are lots of books or standards and tables that can be used in the selection of materials with regards to the its performance in the different corrosion environment. Cost here may be a significant factor, though it is not always economically feasible to employ the material that provides the optimum corrosion resistance. Sometimes, either another alloy or some other measures must be used. Changing the character of the environment if possible may also significantly influence the corrosion, like lowering the fluid temperatures and or velocity usually produces a reduction in the rate at which corrosion occurs. Many times, increasing or decreasing the concentration of some species in the solution will have a positive effect. For example, the metal may experience passivation. Inhibitors are substances that when added in relatively low concentrations to the environment decreases its corrosiveness. Of course, the specific inhibitor depends both on the alloy and on the corrosive environment. Inhibitors are normally used in closed systems such as automobile radiators and steam boilers. The fourth way to prevent corrosion is through design changes. The design should allow for complete drainage in the case of shutdown and easy washing. Since dissolved oxygen may enhance the corrosivity of many solutions, the design should, if possible, include provision for the exclusion of air. That is the reason why in thermodynamics you can see some equipment that involves the part where we can actually exclude or we can exhaust air. Physical barriers to corrosion are applied on surfaces in the forms of films and coatings. And this is our fifth prevention control. A large diversity of metallic and non-metallic coating materials are available. It is essential that the coating maintain a high degree of surface adhesion, which undoubtedly requires some pre-application surface treatment. All three material types, metals, ceramics, and polymers, are used as coating for metals. One of the most effective means of corrosion prevention is cathodic protection. It can be useful in all 8 different forms of corrosion discussed in the previous slide, and in some situations may completely stop corrosion. Cathodic protection simply involves supplying from an external source electrons to the metal to be protected, making it a cathode. This reaction is uh, is in the reverse direction of our oxidation, which is the reduction. One cathodic protection technique employs a galvanic couple, wherein the metal to be protected is electrically connected to another metal that is more reactive in the environment. The oxidized metal is often called the sacrificial anode, and magnesium and zinc are commonly used as such because they lie at the anodic end of the galvanic series. Now that we learned the different ways to prevent corrosion, we can move forward to the corrosion of ceramic material. So far, we already discussed the corrosion of metallic materials. That is why it is also important to discuss corrosion of ceramic materials. Ceramic materials, being compounds between metallic and non-metallic elements, may be thought of as having already been corroded. That is why they are exceedingly immune to corrosion by almost all environments, especially at room temperature. Corrosion of ceramic materials generally involves simple chemical dissolution, in contrast to the electrochemical processes found in the metals. Finally, the degradation of polymers. Polymeric degradation is physiochemical. That is, it involves physical as well as chemical phenomena. Polymers may deteriorate by swelling and dissolution. Covalent band rupture as a result of heat energy, chemical reactions, and radiations is also probable. To briefly cite a couple of examples of polymer degradation, polyethylene, if exposed to high temperature in an oxygen atmosphere, suffers an impairment of its mechanical properties by becoming brittle. Also, the utility of polyvinyl chloride or PVC may be limited because this material may become colored when exposed to high temperatures, although such environments do not affect its mechanical characteristics. Let us dig deeper to the mechanisms by which polymer degrade. First is the swelling. Here, the liquid or solute diffuses into and is absorbed within the polymer. The small solute molecules fit into and occupy positions among the polymer molecules. The macromolecules are forced apart such that the specimen expands or swells. Thus the term swelling. A partial dissolution process in which there is only limited solubility of the polymer in the solvent. Dissolution, on the other hand, is when the polymer is completely become soluble. Maybe because it is already melted or it is already uh, dissolved into the solvent. This is just a continuation of swelling. Polymers may also experience degradation by a process termed session or the severance of rupture of the molecular bands. This causes a separation of chain segments at the point of session and reduction in the molecular weight. Band rupture may result from exposure to radiation or to heat or from chemical reaction. We also have this term weathering. In many polymeric materials, which serve in applications that require exposure to outer conditions, weathering is probable. Under these conditions, deterioration is primarily the result of oxidation, which is initiated by ultraviolet radiation from the sun. Some polymers, such as nylon and cellulose, are also susceptible to water absorption, which produces a reduction in their hardness and stiffness. All of these are generally involved in weathering. As a summary, we were able to discuss the corrosion and degradation of materials, the term corrosion, the different forms of corrosion, hydrogen embrittlement, the different corrosion environment, the different corrosion prevention technique, the corrosion of ceramic material, and the degradation of polymers.